Hi, this video will be an introduction to PyTorch, the most popular deep learning framework for Python that Meta, Facebook created 7 years ago, and it's behind all OpenAI's models like GPT-3, GPT-4, DALL-E, also the Tesla's autopilot, for example, and Stable Diffusion, to name a few of the services, but it's behind many of the AI models that you are using every day. Also, there is another big player in the deep learning frameworks arena, which is the Google's TensorFlow, which was released in 2015, so 2 years before PyTorch, and it was more popular before, but we can see here in Google Trends that year by year, PyTorch has been the most popular framework apparently. So in this tutorial we'll learn the basics of PyTorch, so nothing too much complex, but the first steps in just 10 cells of Kaggle notebooks. So Kaggle notebooks, if you don't know, is like Jupyter notebooks or Google Colab from Kaggle. Kaggle is the most popular data science platform, which was acquired by Google like 7 years ago. And here we can find not only these collabs, but also competitions, datasets, so free data here, also models like pre-trained models, the code notebooks that we'll be using today. So here you can create a new notebook, and also the discussions that are like forums where people ask questions or share experience, and also these free courses that are really nice to start learning from Python to more advanced topics like machine learning, visualization, and other kinds of data and AI topics. So today, as mentioned, we'll be using this public notebook that I've created for this video. So you can copy it and run the cells from there, or you can create your own one and copy every cell from scratch. Okay, so today we'll see how to install and import Torch, how to create tensors and operate with them, how to do automatic differentiation, datasets and dataloaders, how to create neural networks and how to train them with the loss function, optimizers, and creating a training loop with them. And also how to do all of this in GPU, because these Kaggle notebooks allow us to use the GPU for free. So we have 30 hours per week of GPU. We'll see how to do this. And finally, we'll see how to save, load, and use these trained PyTorch models. So let's go. First of all, how to install Torch. So luckily in these Kaggle notebooks, as in Google Colab, it's already installed, so we don't have to install with pip these libraries. But if you want to run Torch in your personal computer or in your server, you can come to this link of here, and you will have here the PyTorch website where you can choose the version, your operating system. For me it's Windows, but you can choose another one, pip, also Python. It's available for C++ and Java, but I think that 90+% of the people is using it with Python. Also, if you have GPU, you can choose the CUDA version. Very important, you don't have to install CUDA before in your computer. If you have installed it before, it's okay, but this Torch installation will be installing CUDA as well. And if you don't have a GPU, you can install it also for CPU with this command of here. So it's also available for CPU. But the main advantages of PyTorch are to deal with GPU. So that's a better option if you have it, like nvidia GPU. So here, after selecting all of these options, you can copy this command of here and run it in your terminal. It can be pip3 or maybe only pip for your case. Okay, so whenever we have installed Torch, it's already installed here in this Kaggle notebook as mentioned. We can run this cell, and maybe the first time that you run it, it will be starting the notebook. So now I already started before, but maybe it can take some seconds, even a minute, to start the notebook session. So don't worry. And here now we have imported Torch, so we can now run Torch commands. Okay, so next step is to create tensors, and tensors are very similar as NumPy arrays, but they can be used in the GPU. By default, they are created and operated in the CPU, but we'll see that there are some options to send these tensors to the GPU that it's very useful whenever we have lots and lots of computation, let's say, so very large tensors that have to be operated together. This will be faster done in the GPU. For now, we are doing it in the CPU, and this is how we create the Torch tensors. For example, sending here the first dimension and the second dimension, like a NumPy array. So if you don't know about NumPy, it's better to do first NumPy tutorial, so learn a little bit the basics of NumPy, but otherwise you can follow along. Also here in these notebook cells, you can copy this notebook as mentioned and run every cell, but you can also create new cells and play around with these things that I'm telling you. So you can check here this tensor that we have created. And for example, one thing that we can do with tensors is slicing them or selecting parts of it, like in NumPy arrays. So with this 0, we are taking the first element of our tensor. With a 1, we will take the second element of the tensor, so the second array of here. And also we can take from the second array the first element, which is this 3 of here. So we can do many of the operations that we can do with NumPy. So the next step is Tensor Operations. We can do very similar operations as we can do with NumPy arrays. So here we are adding the two tensors. Remember that our tensor was this array of here. So it's 1, 2, 3, 4. So here we are adding every element wise. Let's say 1 plus 1, it's this 2, 2 plus 2 is this 4, and so on. Here we are doing similarly, but with multiplication. So this tensor mul that we are printing here is like 1 by 1, 2 by 2, okay, 1 by 1, 2 by 2. And here we have the matrix multiplication with this matmul that is giving these results of here. And there are many other operations, so you can Google any specific operation. The next step is automatic differentiation, and this is a key aspect in PyTorch because this allows the neural networks to improve, so to learn how to reduce the error after every training epoch. So we can do this by, first of all, enabling the requires graph, by enabling the gradients in every tensor. So this will be building a graph of the operations between the different tensors. Then here we can declare y as x to the power of 2. And here we are computing the derivative of y respect to the x. And this is a very simple example to understand this concept. But in reality, in neural networks, this is done across many operations and many numbers, let's say. This is when it makes sense. And also, most of the times we don't do these low-level operations. We use some higher-level operations that are doing this in behind, but it's very important to know these basic concepts to understand what we are doing when we are using like more advanced functions that does this in the backend. And here, if we want to see our gradient, so x is our variable, this one, well, this tensor that has only a single value. But this xgrad is storing the gradient of our operation. So the gradient in this case is 4. So it's like the derivative of our operation. And like this is how the neural networks learn how to improve the parameters, internal parameters of the neural network step after step. So the fifth cell of our tutorial is datasets and data loaders. Those two are not like essential, so we can train models with PyTorch without using these two, but are very helpful because datasets allow us to declare our data, so our data and also labels, for example, our images or our time series data. It allows us to declare it and also do some transformations if needed, and also declare what are the labels in every case. And then data loaders allow us to very efficiently generate every batch of data and also to load it to the GPU and do other advanced functionalities that otherwise we should do by ourselves, like shuffling the data and other advanced methods. So data loaders already arrange this in a very efficient way. So to train a model, we need a data set of data, and also we need to pass this data to the model. And this dataset and data loaders classes that Torch makes us available in here, like Torch utils data, allow us to reduce the boilerplate and do these operations more efficiently. So for example, imagine that we have here this very small and basic dataset that has like these three features. This will be the inputs and also this target. So the first element of every one of the features and the target is the first example. This is the second example, the third example. You can imagine this, for example, I don't know, imagine that this is the temperature of one city, of another city, and another city. So this could be the three temperatures from three cities, and this is the fourth temperature that we want to predict from the fourth city, let's say. It could be many other things, but that's the first example that came to my mind. So this would be the training set. So every one of these features in order to predict the target. So if this were our data set, it is here like a dictionary in this case. So first of all, we create a data frame for convenience. So we pass from this dictionary to this data frame, df, with pandas that we have imported here. And now we can create our dataset class like this. So we create a class, we can call it however we want. In this case, custom dataset, but it could be like city temperature dataset or whatever name that you want. And very importantly, it has to inherit from the dataset class from PyTorch that we have imported here. So it has to inherit from it. And first of all, we have to init our dataset. So we put here the self and also the data frame that we just created here. We will tell that this is the data frame, what are the features and what are the targets. This is one way of doing it, but in this example of here, this will be a very convenient way of doing it. So you can see here that, for example, in features, we are dropping the target class and then doing like this and getting the values. So this will be now an NumPy array of only the features, and here we'll have only the targets. Here, it's very important to define how we can measure how many examples we have in our dataset. And in this case, it's the length of the data frame. So this determines how many instances we have in our dataset. And also we have to create a getItem method. So these are the three basic methods. We can create others, more advanced ones, but we always have to tell the dataset class what is our data, how long is our dataset, how many examples we have, and how to get every one of them like this. So we'll tell that features is self-features IDX, okay? Very important. How we access every one of our examples. So with the index of this NumPy array. So the index 0, 1, 2, 3, and it will know how many indexes are there from this length function that we define here. So it will go from 0 to, in this case, 5, because there are 6 elements. So the fifth one is the last one. And we will transform in here, in this case, our NumPy array to tensor. So every example here will be transformed to a tensor torch array, taking the data in this case as a NumPy array. And also the targets. So the targets are the self targets as defined here. And we are telling also that the features IDX, so the features 0 goes with the target 0, very important. The features 1 goes with the targets 1. Okay, features 0 are these 3, and target 0 is this one of here. And we will be returning for every example the features and the target that now are torch tensors. And this will be automatically taken by the data loader and passed to the model. So we don't have to deal with many of these transfer functions that these classes will be implementing for us. So here we define how is this dataset, and here we are instantiating it. So here we are creating this dataset using the custom dataset class that we define here. And we have to pass the input this data frame, as we put here that the input of our class is the data frame. So here, this df of here is this data frame that will be later used as we define here. Now we can see here the length of the dataset. So let's run this. And the length is 6 samples, okay? The length of the dataset. And also here we have the data loader. So the data loader is this class that we have imported here. And here we don't need to define our custom data loader class. We just can create the data loader calling this class that we imported, telling what is the data set, what is the batch size, and also shuffle true or false. These are two of the most common parameters. There are many other ones, but these are the most common parameters that you want to define. And the batch size will be telling for every train step of the train loop in one epoch, how many samples at one time will be the model seeing. In this case, it will be 2. In this example, we could put the entire dataset because it's very small and so. But if we had like thousands and thousands of images of high quality, maybe our GPU memory only can take up to, let's say, 50, for example. So maybe we have 1000 images and our GPU can take only 50. Here we should tell the batch size to be as large as 50, maybe 45, for example. And the data loader will take care of sending 45 images at every loop of the training loop. And shuffle through makes that every new training will have a different order of the examples. This is useful for training, for testing. We don't do that, but then the model don't overfit as much. So here we can try to use our dataset and data loader to check if it's working good. Doing this like data loader iter, and now we'll have an iter object that we can take every next example. And we'll see here sample X and sample Y. So our data loader, what it returns is this, the features and the target. So we have here sample X is the features, and Y is the labels. And here we can see the examples. So if you can see here, I'm printing sample batch. Maybe let's put here another new line character. So sample batch, sample X, this X. So this tensor of here is our first 2 samples of features of inputs. So this is the first one, feature 1, feature 2, feature 3. This is the second sample. And here's the level of the first sample and the level of the second sample. So this is how our data loader automatically sends a batch of 2 samples to our model. But now here we are only printing it to make sure that we declare everything correctly. Okay, so let's see the next step, which is neural networks. This is how we define models in PyTorch. And we'll see here one of the most basic neural networks, which is a fully connected neural network. And we can import these layers of the neural networks from Torch NN, Torch Neural Network. And here we have to create a class for our model. You can call it whatever you want, simple NN, for example, or my temperatures model, or whatever you want to call it. And here we have to import NN module because we are inheriting from this class of here. We have to define the layers. First of all, here in the init, we have to define every layer that we'll be using. And in the forward step, we will be defining how the information, how the data goes through every layer of our neural network. In this case, we are using the fully connected layer number 1. It will have 2 neurons that have 3 inputs. Then we'll have another layer that will have 2 inputs for a single neuron. is a perceptron, and also the ReLU activation function that allows us to have non-linearity operations. So basically, ReLU function makes that if the signal is negative, it returns a 0, okay? So the input is the x-axis and the output is the y-axis. So for every negative input, the output will be 0. And for every positive input, the output will be that number or another positive number, let's say. You can check more about this in Google and YouTube, but this allows our model to learn nonlinear correlations in our data. So here we are defining them. We are telling what is the layer 1, layer 2, and ReLU. And here we are telling in the forward step how to connect this, okay? So we'll have the inputs going first of all here in the fully connected one, and this will be the output of the first layer of our neural network. Then we'll have this ReLU here. So we put this ReLU between our layer 1 and layer 2, and then the layer 2 will output a single value that will be our target value, because as we have 3 inputs, we have to tell that we have 3 inputs. We'll have 2 neurons in the first layer and 1 neuron to calculate the output, the target of our model. So we can instantiate our model like this. So telling model equals to our simple NN. And here we can print the model, and here we can see the representation of our very simple model. Okay, so to understand better our neural network that we just built, our very basic neural network, we have 3 inputs. Those are not neurons, are only inputs. Then we have a hidden layer here with 2 neurons, with 2 perceptrons. The ReLU is applied after them, okay, but the representation of it is like this because the ReLU is applied from the outputs of the first layer, and then the output of this ReLU is passed to the second neuron, which its output will be directly the target of our prediction. So here, every connection of every input to every neuron has implicitly a weight and a bias here that will be parameters that the neural network will be learning at every backpropagation process with the automatic differentiation that we have seen before. So here, every connection not only is connecting every input or every step with every next step, but also has learning parameters, and those are represented by matrices. So PyTorch internally uses tensors to represent the weights of these connections, also the biases with another tensor, and it's adding and multiplying them like this, okay? The weights are multiplied and the biases are added in every one of these steps. And also here with less parameters, but also those are learned. And with the ReLU, it allows to extract nonlinear signal. And here the output of this cell, so basically taking these values with these weights and biases parameters, so the output is directly the target. And what it does, we'll see now, but in training, it looks at what is the predicted target, what is the true value, what is the label. The difference is the error, how large is the error, how wrong it was. And with the automatic differentiation, it can learn how to adjust every one of these steps to go closer to the correct answer, let's say. That's more or less what we do. So yeah, here we can understand better this fully corrected layer, which is all of this. The fully corrected 2, the ReLUs here after the outputs of the fully corrected one, and how the target is calculated from the inputs using our model, that is all of this of here. Okay, so now you understand better how the inputs travel through the fully corrected one. Here we have the output of the first layer. We pass the output to the ReLU. Then we pass the output of the ReLU to the fully corrected 2. And then this is already our final result. Okay, we already ran all of this. And the next step is the loss function and the optimizer. So to train a neural network, we need those two. And the loss function is this error that I was mentioning before. So the loss function helps us to calculate the error and needs to be differentiable because it will be this function that will be derivating with backpropagation to learn how to improve it. And the optimizer will be the function that allows to navigate this loss derivation to optimize our model, so to go towards a lower error. So the good thing is that also PyTorch provides us many loss functions and many optimizers, so we don't have to implement them step by step, making it available to run in GPU and to be differentiable and so on. So for our case, to predict from our inputs and target, we can use the MSE loss, the mean square error loss. This will be our criterion, our loss function. And our optimizer will be a very common one, the SGD, the stochastic gradient descent. And we call them like this very simply. They have parameters and so on, but this is a very simple way of calling them. And this is the learning rate that is telling this optimizer how fast to go towards the direction of the error. This is a hyperparameter that for every case needs to be adjusted. Okay, so let's go to the next step, which is our training loop. We'll be putting everything together to get our model. We'll put it in train mode like here. and we'll be passing all our data examples 10 times, so 10 epochs that are called, and every epoch will have different batches. So we'll have 10 epochs, every epoch will have all our features and labels, and every batch will have, as we mentioned before, the batch size is 2, so every batch will be of 2 samples with its features and labels. We have to create here the optimizers with 0 grad. So we're starting here our optimizers. And here we are already passing our inputs through our model, getting here the outputs. We squeeze it to have in a single array. Then we pass here our outputs to the criterion, so our loss function. Here we have the outputs and here the labels, and it's calculating for every output predicted from our model that it's starting with random weights, so it will be very bad at the first epoch probably. So it's calculating how large is the loss, so how large is the error. Then we are doing the backward, so we are doing the derivation of our internal weights and biases, our internal parameters, and we are optimizing one step using this backward. So now here we can print the number of our batch and the loss, so how large is the error in that step. And if we run this, okay, I forgot to run these 2 cells of here, the neural network and the loss and optimizer. Remember to run every cell. And now if we run this training loop, we can see that it's very fast because we have very low data, the model is so small. But we can see here at every epoch, we have one batch. So we are printing every batch. And at every new epoch, we are printing this sign of here. So epoch 1, we have in the batch 1 this loss, 14, 15, 42. Epoch 2, and we see that at every epoch, the loss function is getting lower and lower and lower. We could do a plot of this and we will see the loss curve, how it's improving in this case, so it looks good. And finally, it gets like stable, so it doesn't learn further. It's a very simple example, but with more and more data, we could get better results in a real case. Okay, so we have been done all of this so far in the CPU, but if we wanted to use the GPU, and if we had one, as here in our Kaggle's notebook, so first we need to activate it because by default it comes with no accelerator. So here we can come and select. We have 2 GPU options and 1 TPU, which is a more advanced accelerator that we have available. So let's select here the GPU P100. They are telling that we have 30 hours per week, as I told before. So turn on the GPU P100. Okay, here are telling us how much hours we have spent so far of our quota for this week. Now we'll need to restart our notebook because when we change the accelerator, we need to restart our notebook. So let's run again every cell here. Now it's starting a new session. Okay, if you do Shift Enter, you can run every new cell after the other. So let's run them quickly. Now we have CPU, but also GPU. But so far, everything is running still in the CPU. In order to know if we have a GPU available or a CPU, we can do it like this, doing torch, CUDA is available. And now that we have a GPU, it's true. When we were using the CPU before, this would be false. So like this, we can automatically know if we have a GPU. Also, we have another parameter that is torch CUDA device count, and we have only one GPU. If we were using like 2 GPUs, like here, then we will see here 2 device count, and then we will need to select maybe one of them or tell how to deal with them. And also, we can finally know what's the name of our GPU, like this, torch CUDA get device name. And this is our P100 with 16 gigabytes of VRAM, pretty good for being free. Okay, now that we see that we have torch CUDA available, we can tell torch device to be CUDA if torch CUDA is available, otherwise use the CPU. So now here we have our device, and if we create a new torch tensor, this one of here, a single dimension tensor, for example, this could be any tensor. After creating this tensor, we can send it to the GPU. So we are creating it in the CPU as before, but we can send it to the GPU like this. So our torch tensor dot to and device, and if device is GPU, now this source will be sent to the GPU. And also our model, in the same way, we can send it to the GPU like this. We instantiate our model that we created before, it's the same model, and we send it to the GPU like this, to device, and device is GPU again. So now if we run this, you see that we are using CUDA, we are using the GPU. We see that our new tensor that we are printing here, new sample, our new sample is our input 0, input 2, input 3, is in the device CUDA now. And also our model is in our GPU. And now if we run like this, we use our model with our new features, okay? So we train our model before, and we are sending the features into it. So our prediction is this one of here. This is our prediction, and it's in the CUDA. So we can now send it back to the CPU, but now we use our trained model into the GPU. So in a similar way, if we want to train our model also in the GPU, we could use this to method with device GPU in here. So our training loop, we could send the model to the GPU first, and then every new input to GPU before sending it to the model. And then all the training logic would be happening in the GPU. Maybe in this case would be slower because sending the data from CPU to GPU takes some time. And if the calculations are so simple, it's not worth to run them to the GPU. But if our data was so large and our model was so complex with many neurons and many layers with many parameters to multiply and do the backpropagation, then with a very complex model, it makes sense to use the GPU. So the last step will be knowing how to save this model, because we have been training it and also using it to predict this new feature in our notebook. But now if we restart the notebook, we'll lose all of this information, especially our trained model. So if we want to save our trained model as a file, only the weights of it, we can do it like this, torch save. And then we pass here the model state dict. And we put here the name that we want for this file, simple nn pth, but this could be other extensions. And then this will be a file. Let's run this. And here in this output section, we can see the outputs of our notebook. So here now we can see our simple nn path that is only 2 kilobytes. So here we can even download our model. So this is our model file. And now in the next session, if we want to load this model without having to retrain it again, we can load it again here as an input of our notebook. We can pass this simple nn.path file. And then here we will need to declare our simple nn. So we need to define this logic of here. So we need to define the model, but we don't need to train it again. We can instantiate our model here from the define code and then load the state dict. So torch load the simple nn path file that we have here in our outputs. And here we'll see model loads successfully. So it works. Now we can pass again this loaded model to the device, which is GPU, now that we still have the GPU here active. And now we can create a new different input. So to predict with it, these 3 input values. We passed our new sample to device, so to GPU again. So we have our loaded model to GPU, our input to the GPU, and with torch no RAD, because we are now not using RAD to improve the model. We are only predicting with the model. So we have our loaded model, our inputs here, and this will be the prediction. And we can see here the prediction. Now it was 1.5 in this case, so something reasonable. And basically this is how we save a trained model, how we load it. This could be a different notebook, a different Python file to put it in production, and how we can predict new features in the GPU or in the CPU using this loaded model. So that was the basic introduction to PyTorch. Now you can learn more advanced things like convolutional neural networks, or how to deal with more advanced and more complex models and larger datasets. But we have seen so far how to install and import Torch, how to create tensors, how to do basic operations with them, how to derivate these tensor operations, how to do backpropagation of these tensor operations. We have seen how to create our datasets and data loaders to later, when we create neural networks, how to pass this data efficiently and to train our models. Then we have seen how to create the training loop to put all together and create models that learn after every iteration, and also how to do all of this in the GPU and using the Kaggle free GPUs. Finally, we have seen how to save a trained model and how to load it again in a separate environment, being able to pass new inputs. So basically putting our model into production to use it after being trained once. We can use it now as many times as we want to predict new future samples that come without a label. So we are predicting those future cases. So you can find again the link of this notebook in the description of the video. This is the fundamental knowledge if you want to know more about building more complex and more advanced models like LLMs or computer vision, to name a few of them. I hope you enjoyed it. Subscribe and leave it a like if you did, and see you in the next video. Bye bye.